Let's talk about another vocabulary, which is electron affinity. It's the negative of the energy change that occurs when an electron is accepted or taken in by an atom in the gaseous state to form an anion. Yes, we know that anytime you have an element like X and then you add an electron, you're going to get X minus, and any negatively charged species is called an anion. So this is usually accompanied by loss of heat energy. In other words, we say that the process of an electron addition to an atom of an element in gaseous state is exothermic. So what we are saying here is an element like fluorine, which we know is electronegative, it likes to attract electrons to himself. When he receives an electron, he gives you a fluoride, and there's going to be a loss of heat or energy with the amount of 328 kilojoules per mole. We know that fluorine is the most electronegative element, so we expect it to have the highest amount of heat loss. When it gains an electron, he becomes more stable, which is why he likes to attract electron to himself, so that he will have the same electronic configuration as neon, to be isoelectronic to neon. Okay, F minus has 10 electrons as neon, while F itself has 9 electrons. Is going to be changed to F minus, which has 10 electrons, because he gained an electron. So now what you are saying is that if this is the amount of heat energy lost, denoted by the negative sign, meaning heat lost, exothermic process, the positive value of this heat loss is what is going to be the electron affinity. So we can conclude that the more positive the electron affinity value is, the higher the affinity for an electron an atom has. Okay? So compare fluorine and oxygen. When oxygen gains an electron to give you O minus, usually O2 minus anyway. So one single atom, we are comparing single atoms, right? So one single atom of oxygen gaining an electron gives you O minus, and the heat lost is negative 141 kilojoules per mole. So if you take the positive value, it's going to be plus 141 kilojoules per mole. So which one of these two elements will have a higher affinity? Definitely fluorine has higher electron affinity than the oxygen, because he has a more positive number. Okay, he loses a lot of heat in an exothermic way to become stable. It loses 328, while oxygen is just going to lose an amount of about 141 kilojoules per mole. And it's the reason why we said before that fluorine is more electronegative. Electron affinity and electronegativity are kind of similar, slightly similar. And now we are provided a comparison of electron affinities in kilojoules per mole of some elements of the periodic table and some noble gases. So one thing you want to know about noble gases, they do not gain or lose electrons. They don't gain, they don't lose electrons. And so their electron affinity is just virtually not determined, or you could say zero. For helium is 0, neon is 0, argon would be 0, krypton 0, xenon is 0, rubidium is 0. It's kind of, they just not going to gain any electrons. There are a few exceptions. Again, beryllium is not determined, and there's another one more. Magnesium again is not determined to be gaining electrons. Other than that, you can tell that fluorine here has a very high electron affinity. Oh, surprisingly, chlorine is given even higher electron affinity. But you can see that those two have very high electron affinity. They lose a lot of heat energy when they gain an electron. Mostly, we can conclude that halogens, main group 7 elements, or overall group 17, we can conclude that those ones have the most values of electron affinity. Why? Because they are the most, I told you, they tend to be the most electronegative. They attract electrons towards themselves so much to be stable. I just wanted to highlight that. This is just showing variations of electron affinities, but I've already explained that these guys are halogens, and halogens will have highest electron affinity. They will release or lose a lot of heat energy when they gain an electron. Fluorine gaining an electron to give you fluoride loses an equivalent amount of 328 kilojoules per mole, and the EA is the positive of that value, so it is positive 328 kilojoules per mole. Okay, chlorine is slightly higher, as we've seen here, 349 than fluorine. But generally, halogens, main group 7A elements are winning with values of electron affinity. Let's do example 8.5. Question: why are the electron affinities of alkali earth metal, meaning group 2A elements shown in table 8.3 either go negative or small positive values? So we are focusing on main group 2A. Those are alkali earth metals, AEMs, moving from beryllium to barium. So here's the reason and explanation. The strategy to answer this question will include you thinking about electronic configurations of these metals. Will the added electron to such atom be held strongly by the nucleus? That is the question. If not, then it should not happen. The electron should not be added. The valence electron configuration of the alkali earth metals is Ns squared, where N is the highest principal quantum number for the process. Now, if you're looking at a metal, for example, beryllium is in group 2. So the highest shell is going to be 2. Okay. And therefore, the outermost electrons will be 2. S squared will be in the S orbital. Remember, beryllium has 4 protons, meaning it has 4 electrons. So the ground state electronic configuration will be 1s2, 2s2. So we are only focusing on this, which is Ns squared, the outermost shell. So now, if an electron is to be added, for example, I'm using the example of beryllium, whose outermost shell is 2, and the outermost orbital is S, and the S is filled up. So if you have to add any incoming electron, he has to come into the 2p. The electron has to come into the 2p. So take that one electron to be the one that's added. So beryllium plus an electron to give you Be minus. Okay. So this one is further away from the nucleus. Remember, you have 1s2, then you have the nucleus. So you have n equals to 1, you have n equals to 2, and then in the n equals to 2, you have the subshell S with the S orbital and subshell P with the P orbital. So the 2p is going to be further from the nucleus. In fact, if you look at the energy diagram, we always fill up the 1s before the 2s, before the 2p. The nucleus is somewhere here. This is the n equals to 1. This is the n equals to 2, roughly. So if you add an electron, it's added at a higher energy orbital and is further from the nucleus. So no need. Let me see what I can read for you here. The extra electron must enter the p subshell, which is effectively shielded or blocked by the s subshell electrons, the NS electrons are more close and attracted and penetrating than the NP electrons to the nucleus. Okay? They're attracted to the nucleus more than the P because they are closer to the nucleus. These S are closer to the nucleus than the extra P you're adding. This is your nucleus. Consequently, alkali earth metals have little tendency to pick up an extra electron because it's not going to be stabilized or attracted to the nucleus too far away.